we want to discuss diagonalization. Okay, well, before I do, let me talk about why we like diagonal matrices. So if I hand you an n by n diagonal matrix D and the entries D1 through Dn are along the diagonal, we have zeros everywhere else. Okay, immediately we can, for example, compute powers. Here R is some positive integer. And all we need to do, we saw this a little bit at the very beginning when we started talking about how to multiply two matrices, but you just raise the entries along the diagonal to that power, so it's very fast, okay? If we want the determinant, okay, this is an example of, I was mentioning this 100 by 100 matrix. I could give you a 100 by 100 diagonal matrix. You'd have the determinant just like that. Okay, very fast. It's just you multiply the diagonal entries, okay? And sort of related to this, that's why I kind of put them on the same line. Diagonal matrices, we know immediately when you're invertible. You would just need all of the diagonal entries to be non-zero. But usually if you look at a matrix, you can't spot immediately if it's invertible or not in a second, like we can with diagonal matrices. We can also see the rank immediately. It's just the number of non-zero diagonal entries gives us the rank of the matrix. And then one more comment I will make, although I could make more, about what's so nice about diagonal matrices is if you are in the invertible case, okay, well, the inverse is just 1 over, well, it's also diagonal, and you take 1 over each entry, and this is the inverse matrix. You could see that quickly if you hadn't thought about it before by taking this, augment it with the identity, and all you'd have to do to get the identity on this side is multiply each row by 1 over the appropriate d sub I, like this. Okay, very nice. So we see, for example, and this is my whole point, okay, remember we loved orthogonal bases, we also love diagonal matrices. So we love things that look like this because it's very easy, and even though I love math and math can be hard, I really like when things are easy. Okay, so these are matrices that are very nice, but as we know, most matrices are not diagonal, and this is what we want to discuss is the process of diagonalization. A square matrix A is diagonalizable provided there exists an invertible matrix S such that S inverse AS is B, where B is a diagonal matrix. Okay, this is what it means to be diagonalizable. And I will also say to diagonalize a matrix, this is now a verb, means, well, it means you find the S and you find the B such that this holds, okay? Now I need to give you a little bit more terminology here as to what this is. This equation is something in matrices. This says that they are similar matrices. So what this says is that A is similar to a diagonal matrix B. This is the notion of having this invertible matrix S such that S inverse AS is this matrix that's said to be, the two matrices are similar. Okay, that's just another term I wanted to bring up. Similar to a diagonal matrix B. Okay, very nice. Well, we want to understand how to do this and when does this happen. It's not true that every single matrix is diagonalizable. It doesn't go like that. Some are, some aren't. So let's try to unravel this. Okay, let's unravel what this means to be diagonalizable. So you have an n by n matrix A, and we have this. S inverse AS is B. Okay, we can rewrite this as follows. If you multiply on each side this way by S, it reads this. AS equals SB. Okay, it's the exact same equation. But now let me give myself some thing to work with. Okay, we know B is diagonal, so it's going to have the following form. Lambda 1, lambda 2, out 2, lambda. Let's say that's n by n. Okay, I didn't say that anywhere. That's why I was looking, but it's square. Okay, they're going to be n by n. Everything is going to be n by n in the picture. Okay, here's my diagonal matrix, and then my invertible matrix S will have the following columns, Vn, and these are columns. So I'll put little bars to denote these are columns. I could do the same for A as a square n by n matrix, but I'm not going to need it for what I'm going to do. Okay, so let's work with this side of the equation, see what this is, and then this one, and then we will see what happens when they happen to be equal. This is my goal. So we will start maybe with AS. What is AS? Well, this is A times here. One way we can think about this matrix product is the columns of this times this are, well, A times V1 is the first column, A times V2 is the second column, and I forgot my column bars, but it's fine, I'll put them. A times V3 is the third column, and like this. So this is A V1, and then we have A V2, and then we go out. The very last column is A Vn. Column, column, column. Now, okay, so I have an expression, and maybe I need to do this. That's something separate. What about the other one, SB? Well, this is, I will put a little bit less. I'll just put the first and the last initially here, and then times the diagonal matrix. Okay. And then I'll put this. Well, when you multiply a matrix times diagonal in this order, I think we might have done this a little bit when we had a question back in our multiply matrices. Find all 3 by 3 matrices that commute, and I had some diagonal. We multiplied on each side and saw what happened. But we can also just think about what happens when we take this times this in this order. Well, it would also be this matrix times this column, right? And then this matrix times the second column, just like it is here. But then if you think about this matrix times a vector, linear combination of columns, you would get just lambda 1 V1 plus 0 times the rest of the columns. So this first one is lambda 1 V1. Okay? And similarly, the next column we would get would be this matrix times the second column, matrix times a vector, linear combination of these columns, we'd get lambda 2 V2, and then zeros times the other column. So this is lambda 2 V2. And finally, I will just go to the last one, the very last column would be lambda n Vn. Okay. Well, the reason I want to look at it like this is because now look, if this equals this, then this column equals this column equals this column, and so on and so on and so forth. So what we see here, just by looking at A times S and S times B, is we see, maybe I will move over here where I have a little more space to write, we see a n by n matrix A is diagonalizable okay, if and only if, maybe I'll say it like this, A V I equals lambda Vi for some, now I'm going to move a little bit this way to have enough space, for some basis V1 to Vn of Rn and scalars lambda 1 to lambda n. Okay, that's what we see by this. Because why was I able to, I'll put stars here. Why was I able to say that the V1 to Vn was a basis? Remember, we need S invertible. Otherwise, this part doesn't really make any sense, the S inverse. So we need S matrix to be invertible, and that says that it's columns for a basis for Rn. Okay, so we can confidently say this. If you're handed an n by n matrix A, this is diagonalizable if and only if we can find some basis for Rn such that A times each vector is just some, good thing I repeated myself, is some multiple of the vector, lambda I times the vector for each element n, this basis. This is what was equivalent to what I have above. And, okay, this is really the whole topic of this chapter, really. So this is motivating my very next definition. Well, here is the definition of what I just had down here, which came from wanting to diagonalize a matrix. Okay, it says a non-zero, and this is important, non-zero eigenvectors must absolutely be non-zero. A non-zero vector V in Rn is an eigenvector with eigenvalue lambda. Okay, A is an n by n matrix provided AB is lambda times V. Now, these are matched together, so we in fact do say that lambda, I'll put this as a bracket, is the eigenvalue associated to the eigenvector V. This is sort of part of the terminology. Okay, very nice. And what this says is that when you take A times V, well, it's a multiple of V, or A times V is parallel to V. This is what this is saying. If you have V is an eigenvector. And then another part of the definition I will say, that's another part I am defining here, is an eigenbasis for A is, well, it's a collection of eigenvectors V1 to Vn of eigenvectors for A that form a basis for Rn. Now, what we just saw and this sort of calculation that I did down here, I can restate in light of these two definitions. So let's restate what I had below. We showed A is diagonalizable if and only if A has an eigenbasis. Okay? This is what we showed. In fact, we showed more, or the comment was more, is that if you put the eigenbasis as columns of a matrix, this is your S matrix, and the eigenvalues are along the diagonal of your matrix B. This is your diagonal matrix. So just by finding an eigenbasis and the associated eigenvalues, you have diagonalized your matrix. You found S and you found B. Okay? Okay, very good. Now let's do a quick example here. I believe I can fit it. Find all 2 by 2 matrices A, B, C, D with this as an eigenvector. Okay, well, all I have to do is multiply this by this and set that equal to some lambda times this, and then I will be able to figure out what the matrix A must have looked like. This is my strategy in this problem. Okay, here we go. When you multiply this is A plus B, C plus D, and if this is an eigenvector, I want this equal to, well, if it's eigenvalue lambda, say, it would be some lambda lambda, because this is what a multiple of this vector looks like. So what do we see from this? This is quite straightforward. I will say to solve that A plus B is lambda, C plus D is lambda. Okay, so we get, so A and C, there's something, and then we get that B is lambda minus A, and D is lambda minus C. And so the answer here, that all matrices A and C are something, as I said, and we get lambda minus A, we get lambda minus C. And this is for, pardon me, this is for any lambda. So for lambda scalar, this would be the form of our matrix. This is all matrices, 2 by 2, that have this as an eigenvector. Okay. Here's a nice problem to think about the concepts and ideas behind eigenvalues and eigenvectors, and it's as follows. We have a matrix A, okay, n by n, and you have an eigenvector V with eigenvalue 4. Okay, so what we're given, let's just write it, AV equals 4V. And then the question is V an eigenvector for this matrix, which is you take A squared and subtract 5A, and if so, what's the associated eigenvalue? Well, the answer is yes. So first, yes. Well, we will realize it is just by using matrix operations, I should say. Okay, well, if you want A squared minus 5A times vector V, and I need to, so first of all, the answer will be yes. provided this matrix times V is a multiple of V, right? This is A squared V minus 5AV. Well, this is A times AV minus, okay. Maybe I'll go ahead and do this one because I don't need to simplify again. A times V is, where is it? 4 times V. So this one is 5 times 4V. Okay, but now here I use that AV is 4V. And then you can pull the 4 out. This is a property of matrix times vector. Finally, maybe I'll move over here. I will run out of space down below. Again, I use that AV is 4V. So I have 16V minus 20V, which is negative 4V. Okay, well, we see the answer. It's yes, because I have this matrix times V is a multiple of V, and the associated eigenvalue, we see it. Its lambda is minus 4. Okay? Before we get into how do we find an eigenbasis, or even how do we find an eigenvalue and associated eigenvector for a general matrix, I want to spend some time thinking geometrically, which is always a good idea to how to begin. Okay, so first of all, suppose we have A is the 2 by 2 matrix that reflects about the line y equals 2x, and I have drawn this line in red. And we want to ask ourselves, is this diagonalizable? And if so, let's diagonalize it, meaning finding the S and finding the B. Okay, well, I'm not just going to think geometrically, I'm going to do this full problem, which means I will find A, and I will verify, for instance, that AS equals SB. So we're going to try really understand these concepts in this 2 by 2 reflection example. Okay. First of all, let's find A. It's a very nice review exercise. We know the reflection is 2 times the projection minus the vector. This is one way we could write reflection. And to find the matrix, all we need to do is find the reflection of E1, and this will be of the form AB, and then the matrix is AB, B minus A, like this. Okay, well, I guess I will pick, let's see if I do 1, 2 here. Then the line L is the span of W. And then I can get going with this example. Oops, span W. Okay. So now we will find the matrix. Just as a nice review exercise, we take 2 times, this will be E1 dot W over W dot W. W minus E1, which is 2 times, well, here, when you take E1 dot W, you get 1. W dot W would be 1 plus 4, 5, and then times this vector 1, 2, and then minus 1, 0. Now this will be the first column of my matrix, and this is, let's see, 2/5 minus 1, negative 3/5. We get 4/5 minus 0. Okay, and this is the A, B. So my matrix, maybe now that I have this calculated, I will erase this formula because I won't really need it much after this, and I'm trying to leave room on the board for some other things. Okay, so my matrix A, we know what it is. Now that we have found where E1 goes, my matrix A is as follows. Minus 3/5, 4/5, AB, B, minus A. Okay, very nice. But as I mentioned, I don't even need that to think about what's happening geometrically. I just want to actually verify that AS is SB, like this. Okay, what is happening? So I'm trying to think of vectors that are mapped through this reflection to something parallel or a multiple of the vector. And one of them is right here. Oh, in fact, it's almost the same length. So this is my W. Now, let's do reflection. Ready? Go. There it went. Okay, W is mapped to W. Believe it or not, the reflection happened. This one is fixed. So we know A, W is W, which means that we have one eigenvector already, and the associated eigenvalue is 1. S, I can put W in the first column, and B, this is the diagonal, I put the associated eigenvalue here. Okay, so far so good. Well, it is also the case right here. Minus W, that is also fixed, okay, because it's along the line. Or if I did 5W or 10W or minus 0.1W. You don't want to take that as a second eigenvector and put it here, because what we're trying to fill with S is literally independent, right? We want, in order to be diagonalizable, we need two linearly independent eigenvectors for this matrix. So you don't want to pick anything along the line, okay? So now we just have to think about reflection a little more. What happens to this vector? Minus 2, 1. So this vector, I will call it, say, V is minus 2, 1. What happens? Well, it's mapped here. You notice it's parallel, right? When you reflect, and this one I actually do something, you reflect, and you get negative. In fact, because this vector is perpendicular to the line, the formula for reflection, you take 2 times the projection, that's 0, minus the vector. So in fact, you can look at the formula, or you can take this matrix times this vector, and you will see it maps to negative itself, which would be 2 minus 1 here. You can also just think about reflection, okay? So we have that A, V is negative V for this V, which says, and of course, this is not a multiple of this, so they're literally independent, which says we have found a second eigenvector for A. It's this one, minus 2, 1. And the eigenvalue is negative 1. Okay? So in fact, the answer is yes, A is diagonalizable, because we were able to find 2 linearly independent eigenvectors, just thinking geometrically, right? So the answer is yes. And if so, diagonalize it. Okay, we have, it's here. But the final thing I want to do, because this is our first example, is I want to actually check. So let's check. We want to check that AS is SB. Okay, so AS multiplying on one side. It's a good exercise in understanding the statement to check this, and then we multiply here, 1, 2, minus 2, 1. Okay, I get minus 3 plus 8 is 5. over 5, we get 1. And then I get minus 6. Oh, positive 6, positive 4 is 10 over 5, 2. Then I have 4 and 6 is 10 over 5, 2. Then I have minus 8 plus 3 is minus 5 over 5. We get negative 1. 1, 2, minus 2, 1, and 1, 0, 0, minus 1. Okay, well, we get, we're running out of space, we get 1, we get 2, and then we get 2 minus 1. Okay, very nice. We see in this example, we have calculated everything just as a first example to try and understand these statements. Okay, here's my next example, also coming from geometry, which is really what I'm focused on today. And the very next video is when we really take the time and just work with a general matrix. Let's find eigenvalues and eigenvectors like this. Okay, today we're just thinking about the idea. Okay, here we go. We have a plane in R3, a two-dimensional subspace W, and we'd like to find all of the eigenvalues and eigenvectors for projecting onto this plane, orthogonal projection. Well, we have to think. So first of all, what do we know about orthogonal projection? Well, if you are in W, right? If you are already in the plane and you project yourself into the subspace you're already in, nothing happens. It's the identity. 4 vectors in W. So what we see here is that any vector in W is, okay, I'm glad I said that because now I can change. It is not the case, what I was about to say, that any vector is an eigenvector, any non-zero. Eigenvectors must be non-zero. Is an eigenvector with eigenvalue 1. Okay? So far, so good, but there's also some other ones because what else do we know about orthogonal projection? Well, if you are orthogonal or perpendicular to this plane, then under the projection you map to 0. Okay, so any non-zero vector in this, the orthogonal complement, W perp, is an eigenvector with eigenvalue 0. Eigenvalues can certainly be 0, no problem. Eigenvectors cannot be 0, okay, because you can't have, well, you can't have, we're really interested in eigenbases, and you can't have the 0 vector in any basis, okay? Eigenvectors must be non-zero. Okay, so here is the answer, but if we wanted to be explicit about the diagonalization, we could go a little bit further as follows. So maybe I will do this in green, is that if W is the span of, say, V1, V2, and this W perp, orthogonal complement, is the span of, let's say, V3, okay? These are both 3 vectors in R3. Then we know what these matrices are. So then we have the following. We have S, and we have the diagonal matrix B. And S has V1, V2, V3 as columns. And B, Well, you have to put the eigenvalues in order with the eigenvectors. So the eigenvalue I put in the 1, 1 position corresponds to this. These were both in W, so it'll be this. This eigenvector in the 2, 2 position corresponds to, or the eigenvalue in the 2, 2 position corresponds to this vector. And finally, the eigenvalue here in the 3, 3 corresponds to this one. This third vector in W perp had eigenvalue 0. So this matrix and this matrix would give a diagonalization of the projection matrix A. Okay, now I'm just going to do one more. Today's lesson is a bit short. And I thought about making one big video that included more than one section, but I decided to do it in two separate ones. So I'm only going to do one more example, but I will close at the end of the example and kind of touch on what we will start next time. Suppose A is the 2 by 2 matrix giving rotation counterclockwise by pi over 2, or you can also think 90 degrees. And the question is, well, is A diagonalizable, or find the eigenvectors, associated eigenvalues like this if we can. So I will just ask it this way, is A diagonalizable? So we want to think about eigenvectors and eigenvalues for this rotation matrix. Okay, let's draw a picture. So this is rotating this way by theta equals pi over 2. And here's the end of that angle here. Rotating, here's the angle. Okay. Now let's just think. I will write down the matrix in a second, but let's think. Pick your favorite vector in R2, non-zero. I don't know. Maybe it's this one. What happens under this rotation? It maps here. Maybe somebody else has a different vector in R2. This one, okay? Maybe. What happens under this rotation? Right? Okay? Somebody else. Here's what we need to be in class. I said, somebody else, give me a vector. Well, I'm waiting. No, maybe not. We'd be here quite a while if I waited for that. Okay, maybe this one. Well, rotate it. Do you see? We're not, in order for V to be an eigenvector, we need A times V. Well, of course, it's a multiple of V. But what does that mean? It means AV is parallel to V. And let me make this comment. I've said it a few times. So note, and this is generally V is, oh yes, an eigenvector for A. It means that AV is parallel to V. We realize, I will just say through our discussion, that the matrix A has no real eigenvalues. Real numbers is what I'm saying here. And I will make a comment about this in just a moment. Because it has no eigenvectors. Okay, just through this is rotation. But what is A? This we know. The matrix of rotation is cosine theta, sine theta, minus sine theta, and cosine theta. And in this case, we get 0, 1, minus 1, 0 for rotation by pi over 2, 90 degrees. Okay, so this matrix is not diagonalizable. This matrix is not diagonalizable Okay. But there's one more observation or comment that I'd like to make. We just saw this matrix, this 2 by 2 matrix has no real, I put in parentheses, eigenvalues by thinking geometrically. This matrix was counterclockwise rotation by 90 degrees or pi over 2, and there's no non-zero vector v that is mapped to a parallel vector through rotation. Okay, but I want to think about this in the algebra of determinants, and this will really move us into the next topic in the next video, which is how do you find eigenvalues? But, so let's think about something for the moment. Suppose, now in blue, this is general, n by n, it's not specific to this matrix, but I will come back to this. Suppose we have some non-zero vector, and this is Rn, and we have an n by n matrix. Okay, then this statement or equation, AV equals lambda V, is equivalent to, well, just subtract AV minus lambda V equals 0. Or another way to write this, we could write it this way, A minus lambda times the identity, okay, V is 0. This and this, well, and this, they're all saying the same thing. This one, though, I'm writing this as a difference of 2 matrices and then times V. Okay. Now, what does this say? So this equation says that V is in the kernel of A minus lambda I. A minus lambda I is an n by n matrix. And, well, it has some kernel, so to be an eigenvector with eigenvalue lambda, it means you must be a non-zero vector in the kernel of this, okay? Then a matrix A has no eigenvectors or equivalently eigenvalues, provided, well, that this, the kernel of A minus lambda I, is just this for every possible lambda. And another way that, well, what does this mean about the matrix A minus lambda I? It says that A minus lambda I is invertible. Equivalently, A minus lambda I invertible, we need the determinant of A minus lambda I is not equal to 0 for all scalars lambda. So this is a way to say that a matrix has no eigenvectors or no eigenvalues is if this determinant is never 0. Okay, now let me erase this part. Let's see that in this example. And I said this is kind of further sort of opening the door as to what we will move into next time, because in chapter 6 you had some homework of calculating the determinant of things like this, if you remember, practicing determinants. And I even said this is foreshadowing things to come. Well, now we're right into it, although we'll really get into it more next video. But I will, this is my final comment of the day, is think about this matrix. So let's just calculate for this matrix, for this specific. Now I'm going back to this specific A. Okay, A minus lambda times the identity is what? Okay, it's minus lambda minus 1, 1 minus lambda. And the determinant here is, it is lambda squared plus 1. And you see, this is never 0 for a real lambda because, well, lambda squared is minus 1, has no solution. So this is why, right, this matrix here is always non-singular, has no non-zero vectors in the kernel, and that's sort of what's saying this here. So this, looking at this matrix, excuse me, looking at this determinant A minus lambda I and realizing it's never 0 is a way to algebraically see that we don't have any real eigenvalues. We thought about it geometrically first, but you see it algebraically by looking at the determinant of this matrix.